Yesterday we were talking about some Hertz contact stresses and how you get that contact patch, and it's basically an elastic contact between bodies and how we model that. Closely related to that is corrosion fretting. This is something that we see all the time. If you've done any sort of seal inspection or failure analysis, certainly, you will probably see this. And there's a lot of seals out there that don't fail because of corrosion fretting, but there are a lot of seals that if they fail quickly, will have severe corrosion fretting given the short amount of time they were in service. So let's dig into this a little bit and make sure that we understand the fundamental physics behind corrosion fretting, because if you understand that, the rest will make sense to you in terms of the mechanisms. So here are three of the most common examples of corrosion fretting that we see in our seals. Top left, you see a drive screw. These are often used in mixer seals, the HSD series, M461s, HSH. And what you see here is this contact patch where this has contacted the oval slots in the driver. This one on the right, a little bit different. This is an O-ring sealing surface, most likely where a dynamic O-ring rides on a stainless steel spot. And the one on the lower left is an anti-rotation pin. And these are very, very common in SH seals. And you can see this fretting corrosion kind of started here. And this is where the pin would engage the back of the carrier of the stationary seal face, and then it would extend into that hole the rest of its length. And you can see this fretting. Now, some of it is a bit of a reflection, but in truth, you can see this fretting is kind of this knife-shaped stuff here, which is kind of interesting. What that tells you is this pin was slightly misaligned, but still okay. Now, all of these are to scale. I realize that the drive screw is probably just a little bit larger, but this is 5 millimeters. And so if you look at this, kind of gives you a scale at which this occurs. So let's dig into this a little bit more. Now, before I talk about this slide, the reason it's called corrosion fretting is that it truly is corrosion. And it starts off as a mechanical problem. It ends up as a corrosion problem. So if you get into metallurgical analysis, failure analysis by labs that don't know anything about mechanical seals, but they look at the precise structure and they say, aha, this is corrosion fretting. And what you don't want to do is say it's not corrosion. I mean, it's an ethylene glycol, or it's just an error. Well, it is corrosion fretting. And let's talk about why. Now, I've mentioned this over and over and over again. Stainless steel is called stainless because almost instantaneously when it hits air, it forms this chrome oxide layer. And that comes from the chrome, which is in the stainless steel, and the oxygen that's in the air. And they combined chemically to form chrome oxide. And chrome oxide is very corrosion resistant. We know that. It's also quite hard. So you get a surface hardness of stainless steel. It's actually a little bit harder than the substrate. Very typical. And this chrome oxide layer in this slide is greatly exaggerated because the chrome oxide layer is somewhere between 1 and 10 nanometers thick. And so that means it's probably a few hundred atoms thick. I could be a little bit off there, but it's very, very thin. And what that means is if it's removed, like you can take some emery cloth and remove it, it takes very little effort, of course, to remove even really hard chrome oxide because it's such a thin layer. And as soon as you remove it, it will oxidize virtually immediately because all it has to do is grow, like 100 atoms. And so it happens almost instantaneously. So let's see what happens here. This is a very generic drawing. Let's say this is a cylinder, could be a drive pin, and this is whatever surface that it contacts. And both of these are stainless steel. Could be 304, 316, even 416, duplex. And so once they contact, it's not the stainless steel that's in contact. It's actually that very thin layer of chrome oxide. And so this is the direction of force, and this is what creates the contact between the two bodies. And this photo would just be, in static mode. All they're do is they're just forced together. Nothing exciting there. But then if you have some relative vibration of that pin, now this shows, it looks like it's really high vibration. And it could be transmitting some vibration from the machine. It could be translated vibration from a slight misalignment, whether that's in the machine or in the seal. It might not be high speed vibration. It might be, a couple of cycles per minute. I mean, if you think about mixers, they don't go very fast. But the point is it's relative movement. And it's relative movement that's for the most part oscillating, meaning it's a wear mode that doesn't give the surface as much chance to do anything else. And so if you have this relative movement, then what's going to happen is these chrome oxide layers, because they're very, very thin, are going to start to wear each other away. And once you wear a chrome oxide layer away, and this is true really whether it's in air or flooded with something or even lubricated with something, there is going to be just enough oxygen present, even if it's just some residual atomic oxygen in there. And what it will do is wear away the chrome oxide layer. Once that chrome oxide layer is worn away, it will do two things. It will immediately reform the chrome oxide layer, but in this case, you have contact. And what's shown here are all these little asperities that are in the microsurface. And if you have contact here, what you can do is squeeze out any sort of oxygen that might remain, and you're also going to crunch up some of that freed chrome oxide. And so since what you get is very, very deep pits, by deep I mean 1,000 times deeper than the surface, which is again going to be very, 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 very thin. And once this chrome oxide layer is gone, the stainless steel can be easily corroded by just about anything. I mean, salt water that you could mix in your garage will corrode stainless steel if you remove that oxide layer. So that's why this mechanical event is fretting, but it's followed almost instantaneously by corrosion of this exposed stainless steel. That's why it's called fretting corrosion. Okay, let's kind of play this tape to the end. Now, again, this is in relative motion, so what it can do is sweep some oxygen in here, and this chrome oxide layer will reform. Now, when it reforms, it's not all shiny like this. Once it reforms, it tends to be kind of a dark black color. which is interesting. If you called into the spray coating webinar, I showed you what that stripe looks like on parts that we have intentionally coated in chrome oxide. And if you'll notice, it's black. Well, there's a very thin layer of chrome oxide on the stainless steel, so why doesn't it look black? The reason it doesn't look black is because that chrome oxide is so thin that it allows some light to just go through the layer, refract off this shiny stainless steel, and reflect outwards. So as this if this chrome oxide layer was deeper, like our coating, that light it tends to get trapped in there and doesn't reflect out. And if there's no reflection, it looks dark, which is actually the color of chrome oxide. That's why, if we zip back up here real quick, if you look at this fretting right here, and right here, it looks dark. And that's because you truly are looking at a thicker chrome oxide layer. All right, let's go down back to here. Okay, so in this case, we've had rubbing. If you'll notice something else, because this is starting to wear away at each other, now you will get a flat spot on this cylinder, and you will also get a flat spot on the corresponding contact surface. And you will see that on the parts when you inspect them. Now, what happens from here on? Well, there's probably still that same relative movement. It's not just going to go away once you've reformed the oxide layer. And what this means is this will start all over again. It's probably not stopped. It's kind of a continuous process of wear and reestablishment of the oxide layer. And then once that oxide layer is reestablished, you have two very hard surfaces in contact, which also have some little crunched up pieces of chrome oxide. And so that's how that wear accelerates. So it's constantly going on. It can go on until this part is actually locked into this part. You can see this is starting to key in to this. And at that point, you can start to generate heat. You can also get fretting on the walls once this gets deep enough. Now, if I go back to this guy, you can see in this case right here, you see this wall here, kind of this cliff, that is also going to be fretted. You can't tell from this picture, but that's okay. If you were to look at the core, I mean, obviously you can see that this began to key in to the driver slot. And that driver slot, sure enough, had a dark area that was fretting corrosion. But you can also see that now, not only at the contact surface, but now this wall and the corresponding notch, this is probably, maybe 10 or 15 thousandths deep. And so you'll see it on the corresponding part. Now, one last thing. We said this was caused from an O-ring. And in many cases, when you take this O-ring off, the O-ring is undamaged. I mean, unless you take it off after like a week. So you think, how on earth can I get this mechanism from an O-ring? And the answer is, I don't know. No, I'm just kidding. The answer is, if you have relative motion between an O-ring and this stainless steel part, what it can do is this O-ring, a little bit different than this O-ring will actually conform itself slightly to this substrate. But what happens is this O-ring is actually flexing back and forth, kind of like kneading bread dough. But since it conforms to this, guess what it does? Not only is it creating some slight adhesive forces in here, but it's also sealing off any sort of oxygen that might remain in there. And so if it's, what it does is it seals off the oxygen, but remember, it's kind of moving back and forth. It's not going to wear on here because how it's moving is just kind of, since this is kind of gooey, this can kind of move back and forth, kind of like, I don't know, like the tread of your shoes. You can kind of flex those back and forth without wearing them down. And then what happens is every time this surface kind of just lifts off, it allows some air, or I really should say elemental oxygen, to find this and start corroding this. Okay, so what you're seeing is the flexure of this O-ring, but you don't have any sliding. And if you go back and look at this, this is interesting because this is actually the low pressure side of the O-ring. And so what happens is here you get a very definite line, and that's because that's where the extrusion gap is. Back up here, you can see this is kind of messy because that's where that O-ring is lifting and closing, lifting and closing. And so what's happened is this corrosion probably started up here. Let me zoom in a little bit. Man, that's a good photograph, isn't it? Look how damn straight it is. And you can see it's fairly shallow here, and then it gets really deep into here. And that's because any oxygen that is swept under here never leaves. This oxygen might get pushed out again, but it never leaves. And you can see right about here is where it's really deep. In fact, if you look carefully, you can actually see the lathe marks on this, the machine chatter. See these kind of grooves right here? You can't see them here. So you know this is deeper than this. And this has gone on long enough that this is probably, if you did a roughness trace, excuse me, this is probably a couple of microns deep. And eventually this surface will kind of stop wearing, and it will be rough enough that it will now start to split the ID parting line of the O-ring. And that's why you'll tend to see this fretting corrosion, and then eventually the O-ring can no longer flex. This is just too rough, and you'll start to split the O-ring. What a lot of researchers have done they've tried this in all different kinds of environments, air, salt, all different kinds of stuff. And even if this is lubricated surface, you can still fret it, which is kind of interesting. A lot of these studies that I found are on prosthetic implants, like hip replacements, shoulder, ankle replacements, where you might have stainless steel on stainless steel, and it's lubricated by the meniscal juice, whatever that called. Also albumin, which is a cell transport fluid, and even still they get fretting corrosion. So yeah, pretty interesting. That's why a lot of those now are titanium, or they'll be coated with some sort of polymer, and that's to avoid fretting corrosion. Pretty cool. Okay, thanks for calling in. Talk to you tomorrow. Have a good day. Bye.